So I stumbled upon this integral. So the integral was actually like x squared in the denominator, but I said why not you know generically, no wait, no, what's it called, generalize it. Yeah, generalize it. So I was like, why not generalize it? So I just put an n up there, right? And actually, yeah, I'd rather call this I of n, and would find out soon that it's something special. Yeah, I think it's probably in the title, but yeah, yes, we'll see. So basically, I stumbled upon this as like x squared in the denominator, but I changed it to generalize it. Okay, so we do something pretty obvious, I guess. So to speak, I mean, it's a use substitution. I mean, I don't really use u. I use t because I like physics. So we say t is equal to ln x, right? That's a substitution. So just like exponentiating both sides, I guess. E to the t is equal to x, right? We can differentiate both sides. So e to the t dt is equal to dx. Now we can plug everything back into our integral. Okay, so our bounds, right? So as x is equal to 1, t is, okay, so ln of 1 is 0, so t is equal to 0. As x is equal to, x goes to infinity, yeah, I guess t2 goes to infinity, right? Because I mean ln x diverges, but slowly. I think there's like a proof for that and stuff. But yeah, it's divergent basically. Anyways, yeah, t goes to infinity. So our bounds change from 0 to infinity. And there are integrals. Okay, so ln x, right? That's t over x to the n. Well, x is e to the t, so this is e to the t times n. We use exponentiating exponent rules, I guess, so to speak. Yeah, anyways, we use basically exponent rules. Yeah, and then this is e to the t dt, right? The dx is e to the t dt. Okay, so we can simplify this, right? So I'm just gonna do it right real quick. So t times e to the n minus 1 times t negative dt. Okay, so now that's pretty cool already, right? That looks pretty cool. I mean, it doesn't necessarily look any better than that if you don't have much experience with integral calculus, so to speak. But yeah, it looks kind of neat because no logarithms. I don't like logarithms. Just putting that up there. Now we use another substitution. So basically, I know I'm not gonna use u. I'm gonna use let's see. Yeah. How about this? Yeah. How do you write it? I forgot how to write it. You know what? Nah, screw it. We're gonna use sigma. Yeah, small sigma is equal to. Okay, so yeah, we're gonna substitute n minus 1 times t, right? That's a sub. So basically, d sigma upon n minus 1 is equal to dt. Yeah, that's pretty easy to see because n minus 1 is a constant, right? So we don't care much about that. And yeah, nothing else changes pretty much. Oh, wait, yeah. And of course, yeah, t is equal to, wait, no, that's not sigma. Sigma upon n minus 1. Okay. So let's see. Our integral changes. Okay, the bounds. So like when t is equal to 0, sigma is equal to 0, and when t goes to infinity, sigma goes to infinity. I mean, yeah, that's pretty obvious. I guess the bounds don't change, right? It's just pretty much just the same, 0 to infinity. I'm not gonna write it out because the bounds are pretty obvious. And then okay, so t is, well, that's sigma upon n minus 1. Yep, it's e to the minus sigma balls. And then what's d sigma? No, wait, what's dt? That's d sigma upon n minus 1. And yeah, that's pretty cool. You'll see what I'm trying to do here, right? Basically, so I'm gonna bring it up here because this is inconvenient. There's no more space. So yeah, basically I'm gonna write the exact thing out, right? So basically it was sigma upon n minus 1 times e to the negative sigma. That's not 6, that's sigma. D sigma upon n minus 1. So yeah, these two n minus 1s will come out, they're constants and they're multiplied together. And the integral from 0 to infinity of, okay, so this is sigma e to the minus sigma d sigma. And voila, that's now okay. I'm gonna wait 3 seconds. Yeah, I should have guessed it's a gamma function. Okay. So that was a weird pause, but yeah, I needed to do that just to test my audience. I don't know. So yeah, n minus 1 squared. It's a constant, right? So these two multiply together to get an n minus 1 squared, and then we can remove that from the integrand because it's a constant with respect to sigma. Yeah, so again, this is, you can write sigma as sigma to the 2 minus 1 because 2 minus 1 is 1, and that's in the form, so that's equal to 1 upon n minus 1 squared gamma of 2. That's just gamma of 2. That's how you define the gamma function, right? So basically, like, I'm gonna write it up here, I guess, just in case you don't know. The gamma, so gamma of x is equal to 0 to infinity, right? And then it's like, okay, so t to the x minus 1 e to the minus t dt. Yep. And it's also equal to, by the way, x minus 1 factorial. It's slightly offset. I mean, people use the pi function, but I guess it's pretty much the same thing at this point. But you know, this is like more conventional to use. Anyway, so it's x minus 1 factorial basically. So this is gamma of 2. That's going to be 2 minus 1 factorial. That's 1 factorial, which is 1. So basically, after all of this is said and done, we get this result. Yeah, wouldn't you? Like, that's equal to 1 upon n minus 1 squared. Like, that's, I don't know. I don't remember seeing this anywhere, but maybe I've seen it somewhere. I don't remember specifically. Okay, that's pretty cool. Now, let's see. How could we generalize it even more? So maybe this will be the next video, but like, maybe I'll add an exponent up here with the ln or something. Yeah, I'll experiment a little bit. I just don't have much time right now on my hands. So, yeah, it's pretty nice. Oh, also, like, you can just, you know what, let n equals 70. And it's all nice. Yeah, there is no arguing with that. It's all nice. Yeah, pretty nice.